Thank you all for coming. Our tutorial on libEnsemble, on library for managing dynamic ensembles of calculations. I'll be presenting. My name is Jeffrey Larson. Also part of the libEnsemble team, Steve Hudson, John Navarro will be presenting, and Stefan Wild, the main sort of core developers of libEnsemble. But we have many other contributors, some in this call or other people who've used libEnsemble who have contributed. We welcome those kind of contributions as well. I won't be able to see in the chat, or I don't see in the chat usually in my Zoom view. So if you have any questions, please interrupt at any point in time. I'm happy to explain anything clear. But libEnsemble is a Python toolkit for coordinating dynamic asynchronous ensembles of calculations. And the dynamic is really what I think helps set libEnsemble apart from other workflow manager packages. It's designed to use massively parallel resources to help with design, inference, decision problems where, say, the things you're calculating, the ensembles are dynamic in nature. You're going to do something, and then depending on some intermediate calculation output, you might want to decide to change your workflow. And libEnsemble is designed to hopefully make that as easy as possible. But the dynamic nature means we have to make some interesting design decisions to help coordinate the workflows in a dynamic way. We want to make it so more people can use increased levels of concurrency, computational concurrency. libEnsemble uses a manager-worker paradigm. Manager gives work to workers, workers do work, do calculations as a part of the ensemble, or coordinating the ensemble, and gives information back to the manager. And the manager gives out more work. We don't usually consider worker-to-worker calculations or communications, but most things go through the manager to help with the sort of dynamic nature, helping coordinate the manager's in charge of coordinating the calculations. And then what is a worker? I mean, a libEnsemble worker is the smallest indivisible unit. So I guess the number of maximum, concurrent function evaluations you like to run, or simulation evaluations, or whatever part that is. I mean, a worker could have a node, a worker could have a CPU, and the resources given to a worker could be not identical across your collection of workers, but the worker is sort of the smallest indivisible unit. Great, so what does libEnsemble require of a user? The libEnsemble workflow is coordinated by 3 functions. A generator function that generates inputs to something we're going to call a simulation function, a simf, and an allocation function, alloca. The genf makes inputs. This parameters that are going to coordinate, or that are going to determine what the simulation is to be calculated. The simulation can be any sort of numerical calculation. And then the simf is going to evaluate some user-defined function using the inputs defined by the generator. The gen produces the inputs, the sim does the evaluations. And then the allocation function decides, as workers become available, whether or not sim work should be done or gen work should be done. In some cases, the sim could be a very cheap thing, evaluating something, and the gen could be producing some massive mesh, and you want to try to be updating this mesh, and it requires, that's the sort of the numerically expensive part. Or it could be that the gen is maybe just producing some random points in some parts of a parameter space, and then the sim is the computationally expensive part. Or it could be a combination of the two. So the allocation functions could decide between these, or allocation functions could be just sort of very simple in that there's a collection of work and they just keep doing simulation work until the work is done, and then they generate more work. That's sort of the most basic libEnsemble allocation function. But those 3 functions and the interplay between them is what defines a libEnsemble workflow. So I'm going to just walk through sort of the flow of knowledge in a libEnsemble run. Let's just say we're looking at the snapshot in time where I have my manager and I have workers, and one is doing some active simulation and some is doing some generation. We're going to call it persistent generation. And I can explain more about that later, but the generation is sitting there generating the next points to be evaluated while the other active simulations are running, and maybe a completed simulation is also sitting there. And the manager is going to pull very quickly and determine that, oh, the persistent generation is done. It is requested points. I can also, at the same time, take in completed simulation output. I can update sort of what am I doing, call my allocation function, and decide what work should be given out. I'm going to give out that simulation work that was just requested by the persistent generator back to that idle worker. Now I have sort of everybody is active. The persistent gen is sort of waiting for the simulation work to be done. That's why I'm going to call it persistent. It sort of has a state that's just going to sit there, sitting on a worker. And so maybe it doesn't need as many computational resources as the simulation if the simulation is an expensive computation, which is, again, very easily done in libEnsemble. And then when the, say, some simulation output is completed, I can go back to the manager. That information is going to come back, and then I'm going to go to the allocation function, and I can maybe give out additional simulation work and also let the persistent generator know about the output of those other runs that just completed. And so that's sort of a flow in the libEnsemble workspace. This overhead is a little bit, but usually it's fairly trivial compared to the cost of the calculation or some part of the calculation. What are libEnsemble dependencies? Very minimal. We use Python 3.7 plus, NumPy, psutil setup tools. So those are the required things. Of course, there's many dependencies for some of the examples in libEnsemble, but communication in the manager worker in libEnsemble can be done using any of these three communication protocols. The simulation itself could be using MPI or OpenMP or some other form of parallelism to do its work, or the sim or the gen, the user calculations. But that doesn't necessarily conflict with, depending on your system, depending on your MPI, depending on whatever. But you can have the simulation, for example, using Mpi concurrency, and have libEnsemble using Mpi to do the do the communication between the manager and the worker without issue. And our repository contains many example simulations and gen functions that use, say, NLOpt or PETSI or SciPy or Tasmanian. Pick your favorite thing. We could probably easily plug it in to be an example of how we can produce, generate points or simulate points. We access bench simulation function and other ECP proxy apps that are sim functions. And so those aren't necessarily the libEnsemble dependencies, but if you want to run every test that we have, then you need them installed as well. But so what is a user sort of requesting from libEnsemble? Hey, I'd like if my sim calculations or gen calculations can use parallel resources. That's sort of a natural request, and depending on your environment and your sim or gen function, this should be supported. We're able to do this on many of the LCF systems as a part of the DOE Office of Science Labs. A user might request that libEnsemble could terminate unresponsive simulations or generation calculations. Again, something we can support depending on the platform. Termination based on intermediate simulation output. You can observe, say, partial simulation output and determine that, hey, this is a bad set of parameters. I want to stop this simulation. It's hanging, it's crashing or something, and try to get those resources back. We have examples of that. Similarly, the user would want libEnsemble to maintain, hey, what was done when? What were the first points evaluated? What were the last points, and at what times, and with what resources, and how long did it take? And all of that information, performance measures, coarse and fine, we can provide. Simulation or generation checkpointing and restarting. We have examples of that. That sort of, again, depends on is your simulation or gen function supporting checkpointing. We can help recover and restart runs. And then you can take your libEnsemble scripts and with very minimal changes run from your laptop, run on a cluster, run on Summit. And so that's great. And then we sort of envision, say, up to thousands of concurrent workers and have examples of such workflows. Millions of concurrent workers maybe isn't the kind of workflow we're imagining, given that we have sort of a central manager. But you could imagine, say, and we have considered such, say, nested libEnsemble, where there's managers calling other managers that are doing libEnsemble. If that was really a source of interest, we'd be happy to chat about that. But why would you want to use libEnsemble? Just a couple of use cases. Hey, maybe you have a serial code and you want to start running it in parallel concurrently. Or you can add another level of parallelism to a simulation that no longer scales. Maybe your simulation uses a tenth of your computer very nicely, and then giving it additional computational resources doesn't really reduce the time for the simulation to complete its work. Well, you could be doing 10 concurrent evaluations of your simulation at various parameters and be more efficient in your use of computational resources. You don't want to have to write your own tracking code. libEnsemble can tell you when your runs have failed and start other work. You don't want to have to write your own kills for various systems. libEnsemble already has templates for many systems for killing existing runs. You want to add concurrency to a generator. Maybe you have your favorite local optimization method that you'd like to be doing sort of multiple local optimization runs with. libEnsemble can easily support that. We have examples of such things. One use case, I guess, say you're starting a simulation at some random parameters across some domain of feasible parameters, and some causes your simulation to fail. Here we have a particle accelerator simulation that just randomly grabbing magnet strengths to define this particle accelerator simulation causes some unallowable amount of your beam to leave your particle accelerator beam line. And so when that happens, you want to kill such a thing instead of just letting it run to the end. Of course, if your simulation was written in a way where it stopped automatically, that would be nice. But if it's not written in a way, libEnsemble could kill when it observes or when there's output in that says, hey, the simulation is not acting how we want. We know that these parameters are no good. Let's try something else. And then again, you could have your generator could update where you're sampling after discovering regions where your simulations have been failing. And so you could be more efficient in, say, use of your computational resources. When you start finding that your parameters are causing your runs to crash, don't use those parameters or nearby parameters. Maybe you're trying to optimize a function that depends on a simulation. I sort of mentioned this before, and the simulation is using some fraction, but not a large fraction of a computer, maybe a tenth of your computer your simulation uses nicely. You could be doing concurrent evaluations of your simulation at various parameters and try to find an optimization in a concurrent manner. So okay, those are two use cases. If anybody wants to try to clone the repo, I was just going to show a bit about the repository, give an overview of the repository, and get clone. I guess I should do it this way. Oh, that's not what I want. Get clone HTTPS GitHub. Hopefully this should be a recent one. libEnsemble. So it should be fairly fast to clone the libEnsemble repo. Wow. See libEnsemble. And so we have if you want to say, I'm going to go in and show some of the tests or the sims or the gens or the allocation functions. If you go into the libEnsemble directory inside of libEnsemble, you can see there's the gen functions directory, the sim functions directory, the allocation functions directories, and then some other utilities, tools, and tests. And so if you look inside of the sim funcs, you can see some example sim functions, some example gen functions, you're calling, I don't know, Tasmanian, surmise, Bayesian optimization methods, uniform sampling, and then we can go into tests, regression tests, and we have a collection of regression tests that call and show these kind of use cases. And so if you're looking to, I don't know, look at how libEnsemble can coordinate hefty simulations using various parameter strings, this would be a fine unit test or a regression test to look at. So that's sort of a high level overview of libEnsemble. We also have, I guess I should mention, in addition to the regression tests, we have a community repository where people who use libEnsemble to do certain runs are able to add and contribute and share with others their scripts. And so that's very nice. So if person A has a libEnsemble use case, sometimes we consider adding it to the main libEnsemble repository. If it's not appropriate, we can add it as an example of libEnsemble in the community repos, community example repos. And so that's been a nice sort of addition to the libEnsemble world. But that's it for my sort of high level overview. I'm happy to take any questions. Otherwise, I'll have John Luke try to pull up his screen and walk through a simple libEnsemble use case. So yes, people in the chat are throwing it, or sorry, I should have mentioned, we're trying to put strings in the chat if you don't want to try to copy, paste, or type quickly things you see on the screen.
Hi, I have one question.
Awesome.
How do we exploit the scheduling software? So do we submit it as a single job for the batch scheduling like Slum, or is it like you can manage the batch scheduling system within libEnsemble?
Usually libEnsemble is included as a part of your batch submission script. So your batch submission script would be call libEnsemble to run my simulation or gen in parallel. And then we're going to be able to, from there, detect your resources, or if you want to allocate different resources to different workers, we can help do that. But we're not, I have operated in the manner where libEnsemble is sort of on the outside of the batch schedule, and that's also possible. But usually we consider, say, you're going to check out some chunk of a computer, and libEnsemble is going to then be your job. And then within that, you're going to chop it up and use various resources, maybe statically or dynamically.
I'll just add, we do detect the nodes that are in your allocation, and we do manage those resources for you.
Okay, thanks.
Great, that was great. And then Alfred had a question in the chat. It's like, which I don't think is a stupid question. Like, hey, if my code runs already fine with libEnsemble, why do I want to use it? I guess I gave a couple examples, but I would say, if you're not using, if you want to say, if you're thinking of a simulation, say you have a simulation, pick your kind of simulation, and it runs just fine. Maybe you want to do search over parameters for this simulation simultaneously or concurrently. You could imagine doing just individual jobs, or you could imagine doing many of them concurrently and taking output from one simulation to guide your search. Like just optimization is one example. UQ, uncertainty quantification. Maybe you want to do uncertainty quantification in sort of a concurrent manner, especially if I guess the case I'm thinking of is, especially if your simulation doesn't scale to the entire machine in an efficient way. Maybe you don't want to, maybe you don't want to track, maybe your code crashes periodically at certain inputs. And instead of it just hanging, libEnsemble could, on certain systems, stop the process, get the resources back. And instead of just sort of, great, you submitted a 10-hour job to run your simulation, and it hangs after the first hour, and then you just keep going in the run because you don't have your own sort of monitoring software, kill software in place. That's just a couple examples. Ryan, did you have a question?
Oh, sorry, just not muted.
That's okay. It's okay. I saw you. Alfred, did that answer your question? Or if you want in the chat, I can sure respond.
Yes, thanks.
Awesome. Great. So I guess I'll let John-Luc take over here. I'll be back later.
Thank you very much, Jeff. All right, let's see if I can share my screen correctly without breaking everything. All right, can everybody see my first slide?
Yes.
All right, great. All right, thank you again, Jeff. We are now going to transition to a quick tutorial, very quick, to demonstrate libEnsemble's interface as applied towards a very simple toy problem. It's basically Fisher-Price, babies first, libEnsemble routine. These slides are based off the content available on our first tutorial on our Read the Docs page. You're welcome to follow along there, though it is more detailed than these slides. As we've discussed, developing for libEnsemble consists of selecting or supplying usually a minimum of 3 components, although Jeff did mention an allocation function. Those are a generator function, a simulation function, and a script that parameterizes those functions in libEnsemble and then initializes the workflow. We'll describe each of these in detail. Listed here is the basic definition, the interface for every libEnsemble generator function. The first parameter, hin, is a selection of the history NumPy array that contain points or values corresponding to fields that the user decides the generator function should have access to. Oftentimes, this HN contains simulation output that the generator can evaluate to produce new simulation inputs. The second parameter, persistInfo, is a dictionary that is both passed to and returned by the generator in order to help maintain state between generator function calls if a user needs it. Finally, GenSpecs contains fields and settings specified by the user in the initialization script to customize the generator function. We encourage this approach so function hyperparameters aren't coded directly into a function. And so based on this interface here, we've written a very, very simple generator function that produces random samples. Note that here we only use NumPy, but users are free to use whatever libraries they like within such functions. And the only requirements are that these functions adhere to the interface introduced in the previous slide, and that they return an output NumPy array and persistInfo. So in the first 2 lines, we see that we start by extracting our user specifications from GenSpecs, including our upper and lower bounds and various other parameters. We then create an empty NumPy array with a data type that adheres to GenSpecs out. It's into this array that will insert our generated data. And on the next line, we use the NumPy array NumPy random generator object stored within persistInfo to produce uniform random values and store the results in the output NumPy array. The generator function then completes by returning the output array and the current state of the persistInfo dictionary. When this generator function is called next by the same worker, this persistInfo will be passed back. And again, remember, this is possibly one of the simplest possible generator functions. And for maybe a really quick, easy exercise, this should probably take no more than 10 to 15 seconds. Using the generator function code from the previous slide, write a generator function that instead produces random integers using the numpy.random.generator.integers function. We're only going to take probably 30 seconds at most and move on to discussing simulation functions. This should hopefully only be a 1-line change. Okay, in case it wasn't obvious, the solution is just to replace the persistInfo randomStream.uniform function with the generator.integers function. All right. So this here is the definition for every libEnsemble simulation function. And you should notice immediately that the interface is almost identical to that of a generator function, with the biggest obvious difference being that SimSpecs is passed in instead. HN still refers to a selection of a history array as determined by the manager, but usually it contains values produced by a generator function to be evaluated instead. And based on this interface here, we've written another very, very, very simple function. This simulation function creates an output NumPy array with a specified output data type from the specification dictionary, and then assigns the Y field in the output array to the sign of the value contained in X in the input array. Then just like in the generator function, the output array and persistInfo are returned. And just like before, we'll take 10 seconds for a super quick, easy exercise. Using the simulation function here, write a simulation function that produces the cosine of the input value instead. I'm not going to bore us anymore, so we can just move on. Now we can talk about configuring libEnsemble. We typically do this in a separate Python script you call a calling script, since libEnsemble is called after we configure it. For starters, we import libEnsemble, each of our previously defined generator and simulator functions, and an additional helper function for producing the NumPy random objects we used within the generator function. Most of libEnsemble's settings are specified in a libSpecs dictionary. For our simple case, all we need to specify is the number of workers and local communications. meaning that the workers are started with and communicate with the manager via Python's multiprocessing. So all workers will be on the same node as the manager. Next, we configure settings and specifications for our generator and simulator functions using the GenSpecs and SimSpecs dictionaries we previously saw being passed into our functions. The in and out fields inform libEnsemble on what inputs and outputs each function expects. And then the user block within GenSpecs is used to customize the generator function. Recall that we parsed these fields and passed them as bounds during the NumPy random uniform call. And we encourage this, as I said, so that these values aren't hard-coded into the generator function. And we're almost done. Here we use a helper function to initialize persist info so that each worker has its own NumPy random stream object. And then we populate exit criteria with the instructions for libEnsemble to clean up and shut down after 80 calls to the simulation function. Then finally, launching libEnsemble involves passing each of our specification dictionaries to the primary libE function. And then on conclusion, the final states of the history array and persist info are returned, alongside a flag to determine if an error occurred during runtime. And with this, launching libEnsemble is as simple as running the script with Python. So Python my ensemble.py. And then here's some graphed example history output using matplotlib, with entries colored by which worker called the simulation function and a point from a generator function call. And as I said, this comes from the final state of the history array, which is returned by the main libE function after concluding. And then finally, if the system you're running on supports it and you'd prefer to run libEnsemble with Mpi comms, you can make changes to your calling script like above. So then the calling script can be run on Mpi run, srun, or whichever Mpi runner works for you. Note briefly that when running with Mpi comms, the manager process runs on Mpi rank 0, with the remaining ranks being for workers. However, instead of doing those changes, we recommend using our parseargs helper function instead. Using it allows you to run the same libEnsemble routine using either multiprocessing or Mpi. So you can do Python my ensemble.py, comms local and workers 4, or Mpi run n5 Python my ensemble.py, and it'll launch libEnsemble using either of those communication methods. And that concludes the very first tutorial and introduction to the libEnsemble interface and programming paradigm. Does anybody have any questions? Oops. I can go back to a slide if I need to. I'm just trying to see the chat room myself if I need to.
Okay, shall I? There's one question, I think, in the chat. Yes, there's lots of examples in the GitHub repo. Yeah, you can supply in the user, so GenSpecs user, or you can supply any keyword you want to pass in. I think that's the question.
Here.
So yeah, just to clarify there on that last part, first. Yeah, there's a ton of examples, and usually we start whenever someone's like, oh, I have a new simulation I'd like to run, I want to do some random sampling. Great, we'll take the random sampling example and point them to that as a starting point. We find that to be the best way to start out. And yes, so then for if you say I have a sim or a gen or something, you have the say gen specs, the user we pass in. So if you have your own fields that you want, some upper and lower bounds you want to sample over in your gen, or maybe your sim has some parameters that you don't want to say hard code in your call to your simulation, but you want to pass, then yeah, you would have a SimSpecs user field. We don't have a SimSpecs user field here, but every time we call your SimSpecs, you can put anything you want in the user field. If it's a massive, massive thing, then maybe it's slow to communicate, but you could communicate file names or arguments or compile strings or whatever you want inside of your user field.
But the input and output fields can be whatever can be put in a NumPy array, basically. So for some very expensive problems that I played with, and let's say the simulation or the generation produces a an output model that it writes to file, and we want to pass that to the other function, I'll typically put a path on the local file system into the NumPy, into one of the input or output fields within SimSpecs or GenSpecs, so the other function can then know where that file was written and then read it, and then use it to produce more further parameters, or to do another simulation run.
Or maybe your simulation produces some very large output file. I'm working with someone who's doing some ice sheet simulation models right now, and each simulation has sort of a velocity field for millions of points on the ice sheet. And at the end of the run, they want to sort of save that. You don't necessarily need to communicate that. They want to tie sort of the simulation that is performed with the output. And you can do that with whatever hash or file name that you want. But you don't necessarily need to pass that around in libEnsemble. It's not going to be used too much. You can pass around the file name, and then it can be loaded in. Sort of what John Luke was saying. Awesome.
All right. Who goes next again?
I think I'm next. Is that right? Okay, so I'm going to share my second desktop, so hopefully people can see this okay. And hopefully you can hear me okay. I've had a bit of internet trouble this morning, so let me know if you can't. So I'm Steve Hudson. I also work on libEnsemble, but in the Mathematics Computer Science division at Argonne. And so I'm going to start just by going a little bit through the history array, but with the actual code. So the history array, which we often refer to as the capital H, is the central data structure that keeps track of your ensemble. It is a NumPy structured array, so this is a NumPy array with named fields, and each row represents a simulation to evaluate. The fields can hold different data types, and the fields there's user fields and there's libEnsemble fields. The user fields are defined in your GenSpecs and SimSpecs out. And there's a simple example on the right here, and I want to stress this is just an example. So GenSpecs out X here is a positional coordinate, so it's a 2D float, and theta would be here and just an example of some integer input that you might want. SimSpecs out, I've just got F, which is a float, and that's your function output. And again, you could have multiple SimSpecs out. The libEnsemble reserved fields are things that hold things like status information, and that gets set by libEnsemble. There's a few examples here, but there's plenty more in the actual array. So the first step in your workflow, so on the left, you see a shortened global history array. And the first thing will be to call your generator function. Now, you'll see in GenSpecs in here, I have X, theta, and F. But on the first call, we're just requesting points. So we might call it with 0 rows. And then your generator will generate a number of points. That could be decided by something in the generator or passed through in one of those U fields of GenSpecs, for example. And then that comes back and gets slotted in to that history array. So the data structure that comes back is also a NumPy structure array, but it's going to be a subset, both in terms of the rows and columns. And then next step, those points will go out to your simulation function, which will also run on workers. In this example, one row is going to each worker, but you can send multiple rows to a worker. You see libEnsemble has set simStarter to true. And then you will generate your function output, and that will come back and get slotted in. And then the third step is you've run your function evaluations, and you want to give those results back to the generator. And as I think it was mentioned before, that can be done in batch. It can be done as the results come in. And this time, those GenSpecs in are relevant. And in this example, again, just an example, it's generating n new points for every n results it gets back, which is a fairly typical workflow. You also see, you forgot to mention, that the manager will sequentially give sim IDs, which on the manager's array are generally the same as the index. you can set those in the generator if you have a reason to. Now, probably the more popular way for most of our users now is to use a persistent generator. And that is a generator that it will start once, and then it will continue running until either the manager tells it to shut down or it shuts itself down. Maybe it reaches a threshold value. And we have a special helper class that provides send and receive functions. So this is going to spot the difference. So in this case, on the left is your simple random sampler that generates random sample points. And on the right, you see you've added these extra lines, which just set up your persistent support module. And then it uses this send receive function, which will send out your points and receive more. So there's also separate sends and receive functions. Okay, to spot the difference is quite easy because I highlighted it. Quite often for persistent gen, it will start with gen specs in being empty. One exception is if you're doing a restart, you might supply an H0, which is a previously calculated history array. This slide is the same, except I put workers 2 and 3 because worker 1 is running the persistent gen. And this step, when you send the evaluation results back to the generator, you have a new field, which is gen specs persists in. And you can use this to say, these are just the values that I want to give back. And in this case, we're just giving F back because we already have the inputs that we generated earlier. So as for storing your history array, most user scripts write the history array to a file at the end, and we have a helper function to do that, which is in our examples. You can find plenty of those in regression tests, for example. You can also write every n evaluations, but I will say we have error handling built in. So libEnsemble detects any exception raised on a worker or manager, and it will write the history array to file when that happens before closing down. So now I'm going to come on to running user applications. So we want to run your user application unmodified, and we want to do that in a portable way, so it runs on all the different platforms. And the way we do that is to supply an executor. So with libEnsemble, there's 3 executors supplied: the base executor, which will run say you want to run a serial application in place, the Mpi Executor, which is the most popular. And all of these, by the way, will run on your worker. The Mpi execution will launch an Mpi run, and it will detect the Mpi runner for your system. And it's normally pretty good at getting the right one. But I will say anything that's automatically detected in libEnsemble can be overwritten. You can supply all of these things. And then there's a Balsam Executor, which I will mention in a moment. And here's a sort of visual shown in your call-in script, how you would set up and import the Mpi Executor, initialize it, and then you register an app to it. The reason for register app is because if you're using Balsam, you have to register it with a database, and that just keeps things consistent there. And then in your user sim function, say, you can also use it in the gen function, but then you will call an executor submit line. Now you'll see in your register app, you will give the full path of the application and then some sort of name, whatever you want that to be. And then you can use that to run it later on. And then you can just say wait, as you'll see an example in a moment. But you can also do more fancy things like polling to see if the task is finished, looking at the output file, killing, and sort of things that were mentioned earlier. And so this can run on whatever detected MPI runner. As I said, you also, the resources are detected, and I will say a bit more about that in a moment as well. But if you do switch between your Mpi Executor and the Balsam Executor, these scripts don't need this script here doesn't need to change. You just import the Balsam Executor here. And it just shows we support a future interface as well for people who prefer that. And so here
Sorry,
is...
Steve, really quickly, somebody's asking if you can make the slides bigger or go to full screen for the moment.
Oh, yeah, okay. Yeah.
Sorry.
That's fine. Thanks. The Mpi Executor can be used if you can run your application from where the worker happens to be. So this would work on your laptop. It works on most clusters on compute nodes. And also it can be used on what I will call three-tier systems. Supercomputers like Theta and Summit, they have login nodes, they have launch nodes. Theta Cray often calls them MON nodes, but they're basically, so you have login nodes, launch nodes, and compute nodes. And if you're doing, say, an AP run on Theta, that always happens on the launch node. So we can run libEnsemble on the launch node, and that works fine. Now, say you want to run on the libEnsemble itself, on the compute nodes, then you could use the Balsam Executor, because Balsam will run on the launch nodes. It will, when you do the executor submit line, instead of running the application directly, it will submit it to Balsam, and Balsam keeps a database of all those jobs and fires them off and manages that for you. Balsam can also be used to run across different systems, and we won't, well, Johnny will say a bit about remote running later, and we'll have a video upcoming on that. This is just showing a couple of example configurations. Now, the first one is what I'm calling dedicated mode. We sometimes refer to it as central mode. So say you've got 3 compute nodes there, and you wanted to run libEnsemble on one of them and dedicate the other 2 to applications. So you don't want to share libEnsemble and what it's launching. And then you just set this option, libspecs dedicated mode equals true. And then the second example shows, well, let's say you don't use that, you're happy to share, but you can run libEnsemble in a distributed way. We have submission scripts in the repo that give an example of this. And so that way your workers can get co-located with your applications. And say you wanted to, share a large file between them, you could use some local memory resource to do that, for example. So that could be useful in those cases. And this is this is not the distributed script, but this is just, we have a whole bunch of example submission scripts under examples in the repo. And this is one of the simple ones for libEnsemble. The thing I refer people to here is if you're running multiple applications on each node, which we can do on Slurm, you want to have Slurm exact equals 1 to prevent it giving all resources to the first one. There are alternative ways of specifying that, but that's generally the simplest. So now I'm going to come to a very quick exercise, and I invite anybody who wants to try this. The main thing is to run this Forces. And Forces it's a very simple application that does some electrostatic forces calculations, but we're not really concerned with what it's doing here, but that we're using the executor. So I will put this away just for a moment and come here. Now I have this here if people want to follow along. If you're starting from scratch and you want to create a Condor environment, you will need an MPI of some sort to build the forces. So you can, if you don't have that, you can, but you've got Condor, you can use this. If you want to clone libEnsemble like this, and of course you can pip install libEnsemble, but this way we can get to our examples. So change drive from top level, libEnsemble test, scaling test, forces, and forces app. So I'll just go to forces first. Now this is the scaling tests are things that we run on HPC systems rather than the sort of simple regression tests, which generally show a simple workflow without applications. And you'll see a few directories here. So if you go into forces, and then you can build it. There's this build forces script, and it's not a make file because it's a one-line build, but there's a lot of optional lines here that you can use with different systems. It's GPU versions here. But if you're on GNU, you can just run the build script. So the application is now built, and then you'll go up a directory to forces simple. And now we can run like this. And we're using that parse args that Jean-Luc mentioned to specify local comms and 4 workers. And you'll see, hopefully this is big enough, maybe I'll make it a bit bigger. It's produced libstats. So this is an overview of each simulation. It shows the all ran and completed, start and end times. There's an ensemble.log. And this gives login information. You can change the level. But this actually shows your actual MPI run lines, which took place. And then there's an ensemble directory, and you're seeing there that there's a separate directory for each application run, and that's the output from those runs. So now I'm just gonna, I think what I'll do is come to our tutorial, which is here, and I don't know if someone can put a link in for this, but it's under tutorials in the docs, executor with electrostatic forces. And it's a bit easier to see here. So here you import the executor, initialize it, and register the app. Now your gen specs and sim specs, so gen specs, we're still just random sampling because this is just to show the executor. And your sim specs, your in is just an X and your output is just one float. And then when we come down to the sim function, here we get the executor. Now, the executor is extracted from a class variable. It's a bit of magic, but you can get it just like this. And you don't have to change this if you use an Mpi Executor or Balsam Executor because it stores it here always. And our input is both our number of particles, and we're using that for a random number seed, but these are just the arguments to the forces application. So I'm not going to worry too much about those. We submit it here, and then a task.wait will just wait for it to complete. And then it reads this output file that is produced, and from that, it will read the final energy. Now, we can configure forces so that it produces bad runs, and we can detect those from the stat file as well, but we're producing 0 bad runs in this case. Another thing you'll see here is the Calc Status. Now that can be one of these which gets imported. Import one up here from these message numbers, but you can also now just supply a string, and that will be what comes out in your libstats at the end here. Now, I've missed out one bit, which is the line, oh, here it is. So this libspec sim does make, that tells it to make a simulation directory for every simulation. And there are a bunch of other options here. If you come to the libspecs page, you can see directory management options. So popular one is also sim input directory. That would be if you have an existing directory with inputs that you want to copy for each one. I'll Okay, and coming down to the exercise now. I've got this on the slide. Bear with me a second. So this is the quick exercise. The main exercise here is for people to try to run this. That's great if you can do that. I will just, I think I will just go through and do this exercise. So I'm going to open up Forces SimF. Hopefully this is big enough for people to see. And it asks me to launch Forces with 4 processors. So at the moment, this will use whatever CPUs it detects, but I can put num_procs equals 4, and then it will use 4 processors for each one. I just submit. Again, this will obviously be oversubscribing on my laptop. And this time, name your standard output and error to this. So this would be fairly simple. Start a new line and say standard out equals text. Standard error equals standard error.text. That should do that. Incidentally, this is a portable option, which will work for the different MPI runners, but you can have an extra args, which will be an explicit string that you want to add to a particular MPI runner. For example, that would do the same thing. Okay, and oops, share the right screen. Okay, so the resource manager, I will expose these. So yeah, first thing to say, it's already been mentioned, libEnsemble is usually run one job submission, which comes with one allocation of nodes. We have our own resource manager built in, and by default, the resources are divided amongst the workers. We automatically detect and read node lists on Slurm, PBS, Cobalt, and OSF systems. If for some reason it doesn't work on your system or you haven't got one of those, you can also supply a node list file in the run directory, which is just a list of the nodes, one per line. And also, as I say, resource management can be disabled with this option. The specs disable resource manager equals true. And the executor is aware of resources and will use all CPU resources assigned to it if you don't specify anything else. And this allows libEnsemble to run consistently across various platforms because different platforms have different built-in application level scheduling. Some will just run everything on top of each other if you don't manage resources. Some will find a slot, some will queue jobs like, queue, not jobs, but applications like JS Run and Summit will do that. But by having this built in, we can run this very consistently using the same scripts in all of these systems. If you have, for example, say your generator doesn't use any resources, a simple thing you do is use, call it a zero resource generator. So say worker 1 uses 0 resources, like in this diagram. This diagram also shows something running in dedicated mode. And then just add an extra worker. And for those who like to use the parse args, there's a convenience option there, which is sim workers, which some people might prefer because that number matches up with your resources. And it's also dynamic resource assignment. So in this case, you look at the bottom right, you can have special gen specs out called resource sets. And this is the amount of resource that you want to give to your job. So it's a bit like an input. for your simulation. Now, to explain a resource set, if we look at this diagram, we have an example where you have, let's say, 2 nodes and 8 workers. And each node will have a bunch of CPUs, but the limiting factor will be that there's 4 GPUs on each node, which is a fairly typical number. So if we're using 8 workers, we've essentially assigned 1 GPU to each worker. But we call that, what is the number of workers divided by the resources, sorry, the other way around. Resource divided by the number of workers is 1 resource set. Okay, and you also see slots mentioned here, and those are like resource sets, but they're enumerated on each node separately. So then you might, in the bottom right, in your generator function, you might use something to tell it how many resource sets I want for this particular simulation. And you'll see here in the case of SimID8, it's using 2, and they get assigned to available workers. So you're not always going to be using all of the workers. You can see the workers as the maximum number of workers in this case. And that's just showing how things may vary. Now, each worker can access its resource information the same way you access the executor. And so you get worker resources, and then you can extract how many nodes I've got, how many my slots on each node. And there's convenience functions like this function here, set environment slots, and that will just set CUDA visible devices for each worker. And this is just mentioning that it will always try to divide things equally. But if it can't do that, it will round up the number of resource sets. So SimID 16, you've asked for 7, it would get 8, you need to use them all. And there's a couple of options here, split to fit and match slots will both default to true. That says that if, there are, say I ask for 4 resource sets and they're not available in one node, although they would be if everything was free, am I allowed to split across nodes? That defaults to true. Match slots says that I require matching slot. For example here, you don't have matching slots on each node. Match slots is useful if you are using things like CUDA visible devices. But if you're running on Slurm and you're just allowing Slurm to take whatever GPUs are available, then you could set that to false and you might get better scheduling efficiency. So this is a simple example sim function where you extract resources in this way, and it also shows getting the local node count and the slot count. And then it's basically setting it so you're running an MPI application, it's giving, for each slot, it's setting 1 MPI task, and each of those is using a GPU. This is showing simply how that would work if you used half the number of workers. And if you use 0 resource workers, you can also explicitly set your number of resource sets. And then you can also, you can explicitly set the resource sets to more than you want, more than the number of workers. Okay, so I think I've run out of time here. But if you go into the Forces GPU example, you can see an example of the code, which by default will use 1 GPU for each worker. But it's very evident if you, so I'll just say this very quickly. If you go into Forces app, in forces.c, look for the OMP target line, and just uncomment this line. and comment out this line, and then you can compile for the GPU. I'm not going to do that now. But you can have a look in your own time at forces simf, and you can see how this is as in the example I showed. And then in run libby forces, it will show the lines that you can uncomment. There's 3 lines you can uncomment here, which will give you the variable resource alternative. And as I don't have time to show this here, we do have a YouTube channel, which I've just set up. I've only put the first video in it, but that video is an example of using running the GPU example Perlmutter, and I'll probably put one up for Spock as well. I'm just going through the process with that. Okay, and I'll mention that we have some users of WARPEX who are running multi-fidelity simulations. And getting up to an order of magnitude speed using multi-fidelity over single fidelity, and that's using libEnsemble. And here's just some of those links I mentioned. And is there any questions?
Great. I'm just going to quick show another example of libEnsemble that's been very common or used by many people to help with their simulation optimization problems, which is actually sort of one of the first use cases that sort of motivated the development of libEnsemble. But let me share my screen. So I want to talk about the Opossum Generator. Opossum is this asynchronously parallel optimization solver providing multiple minima. That's how you get Opossum. And you want to identify high quality local optima of some simulation output. High quality could just be objective, but it can be more than just objective, depending on how sort of the metric you're interested in. Maybe there's ground energy states for different molecules, and you want to identify multiple local solutions. Maybe you have derivatives of your simulation, maybe you don't. Opossum is a generator inside of libEnsemble that doesn't necessarily require derivatives. The SimF can use parallel resources, but not the entire machine. I mentioned this as a common example. And so then running multiple local optimization runs can be a nice way to sort of scale, increase just another level of parallelism for your simulation. You're running your simulation, it's using parallel resources, but now you can do parallel or concurrent evaluations of your simulation using multiple local optimization runs. An Opossum is a logical way of doing this. It also allows you to use some specialized local optimization methods. Maybe you have a non-smooth problem and a non-smooth optimization problem, a non-smooth objective you're trying to optimize. And so then you can use a non-smooth optimization solver within Opossum. Or maybe you have a stochastic objective, so you can use a stochastic optimization method inside of Opossum. So it's sort of a next hierarchy of optimization methods. Here's sort of a cartoon animation of how Opossum works. Opossum starts off by sampling points in parameter space. I don't know, maybe I sample 10 points. And Opossum's logic is, I'm going to start runs from points that don't have better points nearby them. And that's these red pentagons here. This point has a, this point has a better point nearby it, and this point has a better point nearby it. And these 2 points don't have better points nearby them, better being downhill. There's 3 local solutions. And so Opossum's going to decide to start runs from this. And the neighborhood that's used has some theoretical backing for how it's chosen. But great, we start local optimization runs. Here I think we're starting some NLOpt Bobiqua local optimization runs. And Bobiqua starts by evaluating right, up, left, down. And so you see those evaluations are performed. Of course, in practice, right, these contours can only be constructed by evaluating this. This is an analytic function. In reality, the only way you can construct these contours is by evaluating the function at all of these points, and then making this picture. But in practice, all that Opossum has access to is, say, the function value at each dot, whether it's a square, a circle, or a pentagon. Great. So then you can start these local optimization runs, and in a few, dozen evaluations for this smooth function, libEnsemble is very fast at identifying a local solution. And then Opossum then says, great, now that this optima has been found, I can consider, this is sort of this black square on the right is the best point in its neighborhood being defined by this ball. And is it the best point in its neighborhood? It's not, because there's better points nearby, but as Opossum goes, it therefore samples and decreases the radius. The neighborhood metric is defined by the number of points that have been sampled so far. And so Opossum starts to sample more points. And as it samples, it starts to decrease this radius. And eventually this point will be the best point in its neighborhood, and it'll start a run and it'll find this point. Or maybe another sort of local sample will be dropped here and it's sufficiently better than its neighboring points. And we'll start runs from there. And there's some theoretical backing for why Opossum is working in this way. You can be guaranteed that under some assumptions that it will find all local solutions if there's finitely many of them, while only starting finitely many local optimization runs. So I think that's pretty cool. And then I just wanted to sort of show how Opossum can be run, or an example. I can show sort of pseudocode, or I can just actually go to into libEnsemble test regression tests, and I can look inside of my test persistent Opossum NLOpt. And here is the calling script. It's going to say, this is sort of what defines the call to Opossum. There's some sort of, Opossum maintains a lot of information. Is this point a local solution? Has it already started a run? What is the point on the unit cube? Opossum works on the unit cube. Is it a local min? Is it from a local optimization run, or is it from a random sample point? It does different things with these points, and Opossum maintains this information and can let the manager know this information so that it can help guide its optimization run. It also has sort of many user parameters. The initial sample size, in this case, okay, do 100 initial samples before you start, using some sample points. And I want to do libEnsemble local optimization runs, and there's other constants or tolerances that are passed to NLOpt to let each local optimization run know how to work. And so these are all sort of additional information that from the libEnsemble side, it doesn't matter, but this is just going to define the run and can be given to the generator function in this case. These are the bounds on which this optimization is going to run, and then I can come and run it on this problem. Mpi, here I'm going to use Mpi Communications to do the libEnsemble run. And in a few seconds, because this isn't actually a simulation, you could swap out your simulation or the analytic function for a simulation. It runs and it finds the local optima to within, there's 6 local optima for this 6-hump camel problem that's being optimized. And it finds all of them to very high accuracy in 2,000 evaluations. It starts handful of runs, and some of that's reported. You could also do the same evaluation using, instead of NLOpt with 4 concurrent workers, I could use persistent NLOpt using local communications and 5 workers. And again, I can run here. There's some warnings sort of letting you know what's going on behind the scenes for libEnsemble. And again, 2,000 evaluations were performed in that second or two. And that's sort of the Opossum use case. It's been very nice for, again, particle accelerator simulations, or just lots of simulations, ice sheet simulations. I can name many different classes of simulations where people want to find many local optima. The simulation itself, the simulation landscape is multimodal. And so users want to find many high quality local optima. And so Opossum is a great way to run the simulation concurrently at various parameters, and in some chunk of wall clock time, find multiple solutions simultaneously. That was it for me, for my Opossum. And I'm just going to pass it off to John Luke for just one last thing. I think he's talking about maybe cancellation or maybe Balsam X. I'm not sure. He gets to decide with his limited time.
All right. Thank you again, Jeff. As I transition to the last thing we're going to show off today, everyone's welcome and free to ask questions in the chat and or after we're done, and we'll try to get to them as soon as we can. 1 second, please. Oh, whoops, I did that backwards. All right, everybody see my slides?
Yes.
Okay, great. Thank you again. We are now going to conclude by briefly covering some of libEnsemble's, some of which are experimental integrations with a handful of application and function launching services. These features are intended for users interested in running components of their libEnsemble workflows across systems or in the cloud, or simply those interested in experimenting with alternative approaches for handling their applications or evaluative codes. So to briefly summarize in case clarification is needed, libEnsemble's worker processes call simulation or generation Python functions, and many of which use libEnsemble's executors or other methods to launch applications or other routines. There's the chain, as we've discussed, of workers calling functions and launching applications. So for most systems, this set of workers, functions, and apps fits into two common configurations. On personal machines or systems with MPI configurations that support it, everything runs together on one node, like in the first gray block. But on machines like Theta or Summit, where worker processes can't be located with MPI apps, all of libEnsemble's workers are placed on a service node or single compute node, and the Mpi Executor is used to launch the apps on the remaining nodes. Again, these configurations are sufficient for most users, but this is all flexible due to the integrations we'll now be covering. So this syntax within a simulation function should hopefully be familiar by this point, but a user function that fits into those two common configurations typically resembles this layout, where an Mpi executor is instantiated, an app is registered, submitted, and then the running app or its output is evaluated using the returned task object. Now, for our first integration, which we've discussed, or which we've mentioned a handful of times, libEnsemble also features a Balsam Executor, which can be used to submit application instances to the Balsam service for scheduling at a later time, potentially on an entirely different machine. So within Balsam's documentation, it's described as a unified platform to manage high throughput workflows across the HPC landscape. Balsam is developed by researchers within ALCF, where the Balsam service is also operated. So historically, Balsam has been necessary for libEnsemble users who wanted to run libEnsemble itself on the compute nodes of systems like Theta and Summit, since it isn't possible on those systems for MPI jobs to themselves schedule additional MPI apps. Users started their own Balsam service instances to which libEnsemble could submit apps for later scheduling. But however, recently, Balsam has been dramatically updated and extended so that the Balsam service itself runs in the cloud, so to speak, and users initialize Balsam sites to which users can submit applications from anywhere. For libEnsemble users nowadays, that means that workflows running on one system like Theta or even a laptop can submit applications to an entirely different machine, or the same machine if you'd like to use Balsam's features on that machine. So within a libEnsemble function, interacting with Balsam resembles the following. Balsam accepts application definition classes that contain site and command template fields. The site field specifies to Balsam where to run an app, and the command template field specifies to Balsam how to run it. On the libEnsemble side, we import and initialize a Balsam executor and register a Balsam application definition to it. And then before submitting it, we can use the submit allocation function to reserve resources on the corresponding remote machine. Note that you will need to start a Balsam site on the remote machine and then specify its ID to this submit allocation function. Now, I won't go into lots of detail at this time, but to evaluate the results of a remote application run within this libEnsemble user function, you'll likely need to transfer output files from the app back, and this can be done using Globus, which Balsam supports. Now, for a second integration, alternatively to submitting applications remotely using Balsam, libEnsemble supports submitting user functions themselves to other machines or nodes via funcx. This approach allows users to co-locate their functions and applications on the same machine, but those functions cannot be persistent, and users must adhere to funcx's task rate and data limits. And according to their documentation, funcx can be used to execute functions across a federated ecosystem of FuncX endpoints. FuncX is developed by researchers and developers at Argonne, UIUC, and U Chicago. Similarly to Balsam, FuncX operates a cloud service to which tasks are submitted, then sent out to corresponding FuncX endpoints on separate machines. For libEnsemble users, you need to initialize a FuncX endpoint on a target machine and then note its endpoint ID. And then within SimSpec to GenSpecs, specify this endpoint ID in the optional FuncX endpoint field. And that's actually really it for FuncX. The worker processes will submit some simulation or generation function instances to FuncX endpoints instead of calling them in place. And then note that within user functions like the SimF at the bottom, all relevant imports will need to be placed within the function definition, and any paths will need to refer to the remote machine, of course. And then finally, although this isn't technically an integration, we're experimenting with placing worker processes themselves on separate remote systems. And this should allow users to place functions on any systems without needing to set up endpoints or other services, and those functions can be persistent. But this current interface only supports a handful of workers. So the idea would be that you could start libEnsemble's manager on your laptop and then start a generator function on one machine and a bunch of simulated functions on an entirely different machine, and they all send back data to the manager on the laptop. And here's that experimental interface. But as I said, we're still currently only experimenting, so placing only a handful of workers is currently supported, and all of them currently require having the same file system, though we are iterating on this closely. And that concludes our brief discussion of integrations and approaches towards launching parts of libEnsemble workers remotely. Does anybody have any questions? And I think that also concludes our tutorial today. Thank you very much.
And we hit it on the dot.
Perfect timing, yeah.
Mhm.
I had a question
Yeah.
related to the remote execution. One thing I've tried to do in the past using libEnsemble on NERSC is run from within a shifter container. And I've run into issues there that, as far as I can tell, you can't issue new srun commands within shifter. So I'm wondering, looking at these alternatives, if it might be possible to set up something like Balsam to actually allow you to, instantiate libEnsemble within shifter and then launch parallel simulations kind of outside of the container in that way.
Yeah, I think that would be very much possible. If that container can, on the node it's on, access the internet, then it should be able to submit app runs to the Balsam service. And if you have a Balsam site set up on that machine, then it will actually start its own allocations on that machine, sort of contrary to what we were saying about libEnsemble before. So perhaps you could set up I'm just thinking out loud here, but you could set up like a Balsam or a libEnsemble job to use one node on Summit, for example, and then you can request that Balsam request that check out additional resources on that machine, and then Balsam will submit apps from libEnsemble to those additional resources. And we'd be happy to work with you on debugging and helping set that up if you want to work with us. We'd be more than happy to, since this is something we recently started supporting, and we haven't worked with any users using Balsam and libEnsemble together in a while. So we'd like to work with you if you'd like to work with us.
Yeah, I haven't looked at Balsam very much, so I'll have to check that out and see if maybe that would help in this case. Yeah, I'll let you know.
Sounds
Thanks.
good. Mm-hmm.
If anybody has questions, feel free to shoot us an email. Find libEnsemble online. Open an issue. There's example regression tests. That's usually where I point people to for their first. If they're looking to modify something, if you have a question about which one to modify, has Balsam been ported to Aurora yet? That's a John Luke question. So I mean, Aurora is not available, so.
That's also probably not a me question. That That's a Balsam developer's
I think
question.
they're planning on supporting most LCF systems. So,
Yeah, it's since they're an ALCF app, I wouldn't be surprised if they're on Aurora or they're on a lot of these experimental systems further ahead of time than we are.
yes, I agree.
Who's authorized to use these Balsam sites?
Anybody who, yeah, if you pip install Balsam, which is obviously very easy to do, then you can just start a Balsam site on your laptop using, I think, the literal syntax Balsam site start.
No, I think they're asking who's authorized to use the test nodes. Was the
Yeah,
question.
exactly. Like,
The
I mean,
Aurora test nodes.
so I have access to a few clusters, but there were several in the list that maybe I don't have access to. So does that mean that, like, normally, you know, with my whatever ECP accounts or whatnot, but does that mean I could still use some of them because Balsam runs in this like enclosed environment still on these systems, and you could submit something there or not?
So yeah, there's basically two Balsams. There's the new Balsam 2. Certainly the old one, if you wanted to run it in the way I was talking about, you can, anybody can run that. I think with Balsam 2, isn't it, John Luke, do you still have to have ALCF credentials to use that at the moment?
I don't. That may have been the case a couple months ago.
When I used it, I logged in through ALCF. So you may need those credentials.
Right. Yeah, you may need ALCF credentials currently, but I could always reach out to the Balsam guys and ask them if there's been progress made on that end. Because I think the idea is eventually you'll be able to use the same sort of OAuth system as FuncX or Globus or other packages used for authentication. So then if you don't have ALCF credentials, you'll still be able to use Balsam. But I'll reach out and find out.
Thanks.
Mm-hmm.
Thanks for coming. If Osni wants to drop the record.
Oh yeah. Let's see here. We can also probably give out